Jonathan showed to you is that you start from something fairly simple, in fact something quite minimal. What are the minimal ingredients you need in order to clarify a certain force? And so that will allow you to specialize a model, which is not meant for descriptive realism, in fact far from it, but instead clarity in assumptions to insight. And so all the models you've seen, they are different from one another, and none of them is incorrect, but they give you clarify some line of economic trade-offs that you can see in the papers. Now, of course, the topic of the summer school is to get from the theory to some of the estimation steps you might take once you go to the theory. And so think not just about testing the conceptual implication of the model, which you can do through reduced form. In fact, that's the easiest and most natural way to do it. But to try to devise theories that can be understood quantitatively from data. And so you might ask yourself, and this is what I'll try to do here, it's not meant as an introduction to structural, it's meant as an initiation to structural. Looks almost like a sect, like you're putting the little robes and stuff. Anyway, so as an initiation, I think the first question you might ask yourself is, okay, so what are we hoping to do by doing that? So I'll do two things. I'll give you the idea of what this is trying to achieve. And second, I'll do a somewhat technical talk about giving you how you can proceed and technically estimate such a model. So it's going to be the two objectives. All right? So how am I going to do this? Well, here's a set of literature, and this connects very well to what Jonathan has been talking about, explaining that they are simple agency models that we can actually take to data. And by take to data, what we mean is to quantify the hidden variables embedded in that theory. And by hidden variables, we might mean cost of effort, agency cost, how big is the agency cost. And if you might imagine, this is a question that cannot be resolved by running reduced form. With reduced form, you can answer yes or no. Is there any, in a way you can ask yes or no. Is it big enough to see a trace of it in the data? But you can't say how big it is in dollar terms, how much would we be able to pay to get rid of the agency cost. And so what the structural model will try to do is to answer a more difficult question. And there's always trade-off. You want a more difficult questions, then you're going to have to bind yourself to more assumptions. So there's always a trade-off between, yeah, I'm going to solve an incredibly interesting question, but I'm going to have to make more assumptions to get to that result. And so this is how you start with structural. Let's build a theory which has some additional assumptions above and beyond what Jonathan would make in his model, but in a way would allow us to do things with data that we didn't see immediately with reduced form. In fact, you first run with reduced form, you discover certain patterns in the data, you for sure try to answer yes, the theory seems to be about descriptive of the data, and then you do this exercise. All right, so there are 4 steps that I'll show you. And again, I want to warn you, it's going to be also a little of a technical talk. It's going to be how do you actually do it. And I'm going to do it by example, by showing you via a simple example. And then we'll see together how that works. And then I'll introduce you to three families of estimation procedures that would allow you to estimate such type of models, and not just this particular model, but many models in a fairly pain-free way, in a sense that this would take only about a page of code, but not more. Finally, very important, this is something I got from when I took my Ph.D., the difficulty of theory is solving the model. So you're a theorist, you're going to spend some pain solving models. If you're doing agency theory, you're going to have constraints. You're going to have one IC, one participation. But of course, when you get to interesting problems, as the one we saw today, you could have 3, 4, 5, 6, certain papers have 10 different constraints. That takes effort to see which ones are the one driving the optimal wages. And of course, you can do it by brute force. There's nothing difficult about it. You try which ones would be the right one, then you crank it out. With estimation, we'll see that you can go ahead and solve the model, always doable, but sometimes you don't have to. Instead, you identify the solution of the model from the data. And so the data will actually tell you what people are doing. And so in a way, that will convince you that doing structural can be much easier than doing theory. It depends what type of model you're approaching, and you'll see here that it's actually somewhat easier. All right, so let's get started. So motivation, this is what we were describing for a second. But the big takeaway of that motivation is try to be aware that there are some parameters that are hidden from us. The data is about observables. Not always, but to some extent, many observables are endogenous, they're choices, they're resulting aspects of choices, and what we want to know is the primitive, what led to those choices. And of course, if you want to get to the unobservable, you're going to have to model it because it's not directly observable. As a science, ideally, you want your model, what's being behind the scenes, to be compatible with what you see. And so you'd say if there's a good match, this is the right, it's a good fit, my model's a good fit. So another way you can motivate structural is to try to think about an applied question, and this is what we do as applied scientists. Think about a practical question that could not have a complete answer with just a reduced form regression. And I think this is something you'll hear from a lot of experts in this literature. If you can answer a question with a regression, then probably the regression is the right instrument. It's a lot more robust, and it tends to require a lot less description, it's less complex in order to get the answer. So it's very important, you want to motivate structural to ask a question over which there would be disagreement even from a good empirical reduced form design. Here is an example. If someone gets paid more, is he getting paid more because he's getting a rent? Is he get paid more because he's got outside options that he actually is using to negotiate? Or is he getting paid more because he's more risk averse, or maybe the riskiness of the performance measure, as we saw today, has increased? Now, in reduced form, you're only going to see increase in pay. And so you're going to try to see, oh yeah, we see increase in pay. We also see increase in pay for performance. Is it enough to give you more risk premium? Is it too much? And here you try to match different pieces of evidence. Are we having non-commensurate increases in pay, despite the fact that pay for performance increased, but not so much? So when you match those magnitudes, the theory will allow you to say, yes, that should be what's driving it. So I'm giving you that example. There is a recent paper in AER, 10 years old now, that actually estimated models of CEO compensation and tried to explain why has CEO compensation increased over the last 20 years. And the model does suggest that it was related to greater risk. Not more rents, not more outside options, but just the riskiness of all these firms has increased. This is a quantitative answer. You know, the theory could say many things, but then you narrow it down from the facts. As I was showing you, so John showed you some of the work that Chen has been doing, but this perspective on estimating contracts is growing. It doesn't just have to be optimal compensation for CEOs, but if you try to get the sense of how this theory works, you could use it in many other places like debt contracts or other types of financial contracts. All right, so long introduction, but I want to get into specifics. And to make the point, I preferred, rather than be fully general, and you have lots of notations, I want to keep it to the minimal model of agency. And we've done for 3 sessions the risk-neutral model. Now I want to do the same, but with a risk-averse model. The good news is that the same intuitions are there too, and many of you have seen it before. So let's begin with a description of this agency problem. There is a cash flow. Let's call it X tilde. And this cash flow has a PDF. And we're going to say that the PDF is X given A being effort. Let's normalize the effort, and you'll see why I call it 1/2. But let's say that A equals 0 is low effort, and A equals 1/2 is high effort. All right? So they are always binary in this model, binary levels of effort. Let's assume, and for now we're going to take a very specific functional form, but you'll see later that you could certainly extend this. But for now, let's assume that X given A is exponential, and that the parameter of that mean of that exponential is going to be 1/2 plus A, and this is going to satisfy what John was describing as a likelihood ratio property. If A is greater, then the likelihood ratio will be higher for good news. So you see an effect on the likelihood ratios, and so high events will indicate high effort. This is what we want to stay within the classic model. Now let's assume the agent is risk averse, and what he's got is an exponential utility. And so you take this negative exponential form, or Cara, and then you say, well, he's getting minus E of minus R times how much he gets paid, which we'll call y, minus the cost of effort. And let's say the cost of effort is 2CA, all right? So C is the cost of effort, R is risk aversion, and Y is pay. So we've pretty much almost fully described the problem. The only thing I got to say here is and A is not observable. So what the principal wants to do is to design a Y that depends on X in order to induce the agent to work. So in this simple problem, we have two constraints. The first one is that the agent must choose high effort. And so what you're going to see on the left-hand side is going to be if the agent does what he's supposed to do, he's going to get Wx. This is what you see here, minus the cost of effort. Remember, A is 1/2. So 2 times 1/2 is 1. So he pays minus C for the effort the way we specified it. And is going to get the distribution conditional on high effort. No, again, high effort is 1/2. It's going to get f of x given 1/2, and you integrate his expected pay, his utility from the pay, over this distribution. Suppose instead he doesn't do the effort. Of course, what changes now is that you're going to have fx conditional on 0. This is what you see here. But now, of course, the good news is that you're getting Wx, but you're not getting the minus C, right? So you're seeing that there is a cost and a benefit. You don't pay the minus C. That's good. But you're getting a worse distribution, which is f of x given 0. And since Wx will be increasing, that's not good for you. So that's the IC, and that must be satisfied, of course. In a risk-averse model, you, of course, would like to pay the agent minus infinity all the time. That'd be great, because you have no bound on the exponential. And so we usually tie it down by saying there is an outside option. And for our purpose, make it easy, let's normalize the outside option to 0. So he can get 0 by not working. Now, when you see that, by the way, we're in the case of a pedagogical type of approach. But of course, if I were to write a paper like this, you'd say, hey, I don't know if agents have 0 outside wage. Why don't we estimate it, right? Not a problem. Then we'd have to have a parameter here that would play out the outside wage. And so you might be able to identify what this outside parameter is, right? So here we're keeping it to the minimal number of parameters for the sake of keeping it small. Now, you want to induce high effort. Of course, the principal is getting the expected x conditional high effort. And he's paying the cost of the contract. So the cost of the contract will just be the expectation of Wx. So what I'm doing is integrating away all the Wx with a distribution f of x given 1/2. All right, so we have a minimization problem subject to two constraints. Nothing really surprising here. And we know, but also we don't need Ohmström. We know because it's immediate here. But the two constraints must be binding. The participation, if it was not binding, then I could just reduce the whole wage schedule by a small amount, and I'd be fine, but I would make more money. So just reduce it by epsilon, and I would bind. As to the IC, it must be binding because remember, my agent is risk averse. And so if it was not binding, then I would flatten it a little bit, and my agent would be better off. Another way, by the way, if you want to show that things are binding, is even simpler. You write the Lagrangian, and then you take a derivative, and if the IC was not binding, that means that the solution to that problem would be just flat wage. All right, let's write the Lagrangian. This is what I want also to do, a little bit of technical here. So when you see a maximization with two constraints, there's only one thing you want to do, which is to write the Lagrangian associated to that problem. And so what is a Lagrangian? I write the objective function in the minimization. Then I minus a multiplier times the first constraint and another multiplier times the second constraint, right? So let's call that L. And I want to convince you that this is a very mechanical thing that we do when we face any maximization. Regardless how many constraints, you just write it down. And you'll see, objective on the top, lambda is a multiplier for the participation constraint. Within is a constraint set to 0. So you see the IC minus 1, and the PC minus 1. So this is what you see here. This is this constraint for the PC here. And for the IC, which has a multiplier mu, you see the two sides of the IC, and you always write them as zeros. Again, for some of you who haven't seen that before, this is very standard. All right? And now we know that if we want to solve that problem with a Lagrangian, then we can just, remember, we want to find the optimal W. And so what we'll just do is say, my optimal W schedule must maximize the Lagrangian. So the only thing I got to do is to take a derivative in Wx of the Lagrangian. I know how to differentiate, right? I'm differentiating point-wise all these functions. So this is what you see here. This is an optimality condition. So I take my L, I differentiate with respect to Wx, and what's good about it is that integrals are like sums. So I'm essentially differentiating inside the integrals, and so every Wxi is different, and so all my integrals will drop, and I know that point-wise, this equation must be equal to 0 just by taking a derivative on Wx everywhere, all right? So once I'm done with this, I have an equation, a functional equation, and this functional equation is telling me what my Wx should be, right? Okay, so I could stop here. No, really, we could stop here. And I want you to think for a minute and say, all right, so suppose I'm an empiricist, I'm doing some structural estimation. What could I do without going any further? What could I do to estimate such a model? Well, the answer is I might do it without doing any work. Look at this equation. What you have here is a relationship that's connecting Wx's. Now, Wx's, you see them in the data. You got a data set of lots of wages. If you have CO compensation, you get lots of compensation. If you do CFOs, if you do someone, an agent, you're going to see a column of W's, right? What else do you see in the data? Well, in the data, you're going to see X's, right? You're going to see X's, realization of the performance measure. Could be earnings, could be price. Of course, this one has only one performance measure, but you could make it multivariate. Where is X? Well, we don't have X's here. We don't, but actually we do, because fx given 1/2 is the PDF of the exponential, right? So what if I substituted in the PDF of the exponential? Instead of seeing f of x given 1/2, what I'd be seeing is 1/2 exponential of minus 1/2 of x. I would be seeing the PDF of the exponential. So what's behind this object is really an exponential form of x. Same thing here. What about f of x given 0? Well, this is an exponential with mean equal 1/2. I can just substitute in the expression of that exponential with mean 1/2. So when you think this f, you're really seeing a closed form expression of x. So what do we have? I have an equation that's true for any w and any x. And then I've got a bunch of stuff which is not observed. What is this? It's going to be lambda. It's going to be r. It's going to be mu. And it might be the cost of effort that's inside my utility function. So I've got a bunch of parameters I'm looking for. But remember, I've got something that's true point-wise. So what if I looked at the value of those parameters, mu, r, that made the data as close as possible to verifying that equation? In other words, I plug my data in, I square it, and then I say, please, computer, find those parameters that make the sum of all these squares point-wise to be as small as possible. And this is what structural estimation is. You have a theoretical restriction, and you're trying to seek what unobserved would make that theoretical restriction be verified by the data, right? As you will note, we did not solve the model. We're not solving the model here. We just took a derivative. We just solved for the optimality of the wage function, but we didn't solve for the multipliers. In fact, what we're doing, if we did fit that data immediately, is what we'd be doing is trying to let the data tell us what the multipliers are. They're asking the data to tell us. All right, so I want to do two things. I'm going to show you why we still rely a little bit more on theory. That would be a little bit lazy to stop here. So I'm going to do two things. First, I'm going to show you that sometimes you can pin down some parameters so that you search over fewer parameters. Maybe there are some multipliers you can pin down a little bit better by using theory. And second, I'm going to show you a technique that is really nice. It helps you kind of calibrate a structural model. Not always doable, but certainly doable here. And the technique I suggest is the following. If you can solve your model, what you can try to do is simulate data from the solution of your model. So this is made up data, right? So you simulate some data from the solution of your model, and then you seek, is it true that by estimating, by fitting this function, do I get back the numbers that I used to simulate my data? And so you're working as someone who is solving a theory, generating data from his theory, and I'm checking that, of course, you know which parameters you've sampled, but then what you can do is see if your estimation procedure actually works. And so this is showing you that there's something going on that in ideal data it would work. If it works in ideal data, then if the data generating process in practice is not too far from the ideal data, it may give you some confidence that it's actually doing what it's supposed to do. All right, so let's get going. First question, still too many parameters. We've got lambda, we've got mu. Is there a way we can reduce the parameters we're looking for so that we don't let the data tell us everything? We also use more the model restrictions. So one thing you can do, which is very tempting, and this is again something that you learn to do as you do more and more theory, if you've got a pointwise equation that's true like this, so it's a function of x, right? It's true for any x. There's usually two things you'll do. Number one, you can differentiate. Number two, you can integrate. You want to do that. You feel like, oh, let me differentiate that. And if I differentiate, that's going to be nasty because I'm going to have f primes. Now, of course, there is exponential form, so maybe it look good here, but in general, I don't see where else differentiation would help me. What I can do is integrate it away. So I take integrals on both sides of that equation, and I integrate with respect to x, all the x's. And so this is what you see here. Essentially, this is not more than integrating with respect to x the entire equation. And here, some major simplification occurs, which is giving you some of the magic of the exponential form, and that's why in this literature people use the exponential form. So let me show you. First I integrate the density f of x given 1/2, right? So that we know. Densities, they must integrate to 1. That's a property of all densities, so it's going to be equal to 1, right? This one is easy. Then we integrate this term here, which is the utility of the agent on the equilibrium path, right? This is what it boils down to. I'm integrating his expected utility over the entire equilibrium. But we know what this is equal to because the participation is binding. So we know that on average, if I integrate this term, it's going to give you my binding participation. And we know this is 1 from the binding equation we had right before. From this equation that you see on the top here, right? So that also comes out very nice. All the W's, the nasty mess of W's goes out. You got 1 here, 1 here. And in terms of the second part, so this part is the same, also equal to 1 because of the IR. It's the same expression that comes into the IC. And the last one is this one. And in fact, if you integrate the utility conditional on no effort, this also should be equal to 1 because remember, 3 things must be equal. He must be indifferent between leaving, getting 0, not leaving, doing the effort, that's from the individual rationality, and not leaving, not doing the effort, and that's the IC. So this term is also equal to 1. And so what you end up with is 1 minus lambda r times 1 minus mu r times 1, and therefore lambda equal 1 over r. So why do we bother here? Well, it's nice. We've reduced the parameter space a little bit, and we did it with something useful because we're imposing the discipline of the model to tell us this multiplier is actually, we know to what is going to be equal. Step back for a second. This is another thing you could do. I'm not sure my theory is correct. Maybe exponential is crazy. What I could do is try to estimate that equation on the top, right? I could still estimate it by nonlinear least squares. And then I could look at my lambda hat, and I could look at my r hat. But according to the model, lambda hat should be equal to 1 over r hat. Is it going to be close enough? Is it sampling noise enough to explain it or not? If it's not, then my model restriction is not satisfied. That would be a violation of what the model says should be true. So this property is a classic, something you'll see in many papers using exponential. Essentially, the lambda, the participation being 1 over r, is going to be true in any exponential model. And what these exponential models do is that they say that the outside payment doesn't really matter. How much is the agent going to get from outside is not going to affect any of his incentive to participate to the contract. Just move the entire contract up and down. And so the participation will be only related to his risk aversion, the lambda, the multiplier with respect to participation. So that's good. Essentially, once we have this, let's finish up the job and try to not act as someone who estimates, but try to solve the model completely. So what we'll do next is try to solve the model completely. And in order to do so, we're going to have to pin down the remaining endogenous variable, which is mu, right? We don't have mu yet, and mu should be something that's derived endogenously. All right, so let's do that. Again, we didn't need to do that for just estimation purposes, but if I want to simulate data from the model, I need to pin down what mu is going to be. Yep?
So let's assume that we have a very general distribution with parameters.
Mm-hmm.
We could potentially use one of the restriction equations, like lambda equals 1 over r, to determine what these parameters are to fit the data better using just like a random.
Yeah, this model is really beautiful. This is the work by Gale and Miller, and they've. I mean, I really recommend those papers you see at the beginning. They are not that too difficult. They're hard, but they're not horribly hard. This is the answer. So if you have a parametric form for f of x given 1/2, suppose you know it's truncated normal. Suppose you know it's a big family of distribution, but you've got a finite number of parameters to describe it. It's okay because you'll have an infinite number of w's and x's. And you'll have only a finite number of parameters to fit the distribution, so you'll be fine. Your degrees of freedom will still be there. You'll be able to minimize and get it to work. What Gale and Miller show you is something surprising. They say, they prove formally, if you didn't know anything about f of x given 0. F of x given 1/2, you know because it's in the data. That's a distribution of performance measure. But f of x given 0, you don't observe. This is what the agent would have done if, and what they show you is if you don't know anything, so you're trying to identify this, then the model is not identified. Meaning, give me a risk aversion, I'll cook you up an f of x given 0. Give me another, I'll cook you up another, and on and on. And that's of course a problem because different risk aversions are not equivalent. If the risk aversion is super low, then the cost of moral hazard is 0, right? If R is huge, then the cost of moral hazard would be huge. And what they show you is if you want to take this model seriously, you're going to have to do something else, parametric, or you can read the work of Chen and others to put some more restrictions into the problem. Something that's mainly lost a little bit in applied work, lack of identification is important, not because it's telling you what not to do, because it's telling you what you need to assume. You know, you want to answer a question, this is what it takes. And so here I've solved, of course, the problem with a very simple parametric form. And by the way, in their own paper, in the AER, they assume truncated normal. So they're aware of that result, but in the Gale and Miller AER, they make it everything truncated normal. All right, so let's keep on going. Of course, don't hesitate to interrupt. I'm not going too fast, right? I'm going quite slowly. All right, so take the equation you have here, substitute it lambda equal 1 over r, plug it back in the above equation, right? Take this lambda, plug it in here, so my lambda goes away, and then rewrite that equation to write wx equals something, right? So this is what you do if you have this. Rewrite wx, or rather e of minus r wx, and this is what it shows up after you substitute in the optimal lambda, all right? All right, so once you have this, then essentially you have an equation that will help you try to pin down what mu could be. All right. So what can you do here? What you can do is integrate on both sides. Again, I told you have an equation that's true pointwise, and when you have an equation true pointwise, again you're back to saying I want to integrate it out to see what it says. So what I did here is a minor algebraic steps in order to facilitate integration. By the way, absolutely unnecessary. The computer would give you a mu just by integrating the first one. But I want it to look pretty, so as theorists, we always want things to look pretty, so it looks overly complicated. So instead, I integrate both sides of the above, and this equation integrated looks like this one. So 1 is equal to this integral here. That's great. One equation, one unknown, right? You've got one equation, and you're looking for mu. And so what you can do is, if you know what the fundamental parameters are, you know what R is, you know what C is, then calculate its integral and try to find what mu would be. So again, what have we done here? We are not acting as empiricists. Here we're acting as theorists trying to tell you what the optimal contract would be as a function of some primitives. All right, so essentially, if you give me R and C, risk aversion, cost of effort, I will give you mu. And once I give you mu, I can give you the WX from the equation above. I can give you what the wage is. Well, let's be more concrete. If you take risk aversion equal 1, constant absolute risk aversion equal 1, if you take C equal 1/2, cost of effort, and you plug it all in, you solve that integral here, ask the computer to get mu for you, just a minimization. You get mu equal 4.59, and then plug the mu back into my wage equation, and then my wage will be equal to something like this, a log of some exponential form plus 1/2. So you're going to have a function that's semi-linear log form, and so essentially you know what the wage looks like. All right, so what can you do there? And this is where it gets nice to mix together theory and structural. What you can do is simulate a data set. So going back to what we were doing before, take some x's, sample your x's from the exponential distribution. Now, in equilibrium, he does the effort. So the exponential with mean equal to 1. This is the equilibrium x's. Then plug them in my w function and generate some w's. This is made up data, but we're not trying to estimate the real world here. What we're trying to see is, as an econometrician, would I be able, by seeing this data, to identify what R is, what C is, and what mu is? It would be a good thing to do, and in fact, I could do it for different R, C's, and mu's, and implied mu's, and ideally, I'd be able to always recover the right equations here. All right, so this is what this looks like. You simulate this data, and then what you will try to do is to recover R and C. What I'll show you is 3 things that you can do. When you do estimation, there's never a single way you can do it, and it's usually in finite samples really hard to see what's the best way, except by this type of simulation. You can always say, I understand the true model of the world, let me see which one gets those parameters right. Let's begin with the first one. The first one is a version of what the macroeconomists would call a Euler method. And a Euler method in macro is a marginal utility of consumption of today versus tomorrow. That's not what we're doing here. We're doing marginal utility of consumption between states, between x's. But we know from De Breu that marginal utility between states is the same as marginal utility between periods. Just rename states and periods. So what this amounts to, you know from the model that W must satisfy that equation. The problem being that now you're a little bit thinking with two minds here. As an econometrician, you don't remember what mu is, what R and C is, and you want to know if your procedure will get those 3 numbers back from the data set. So what you can do is, well, as we were describing, let me take my simulated WI and subtract what my W of xi should be according to the data. So according to the model, So I take my simulated WI, and then I compare it to my W of xi that you see up there, which is saying what according to my theory the thing should be. But again, I haven't used knowledge of R, C, and mu yet. So ask the computer to minimize this expression, and again, do it pointwise, because as you know, the theory holds, in that case, pointwise, and then try to get these 3 parameters. Here you got a lot of degrees of freedom, because you're only looking for three parameters. All right, so if you do that, I'll post the code so that you're convinced, but believe me for now. It works for most codes, but not always. If you maximize the wrong way, you take the wrong optimization, and you might not always get it. It's more sensitive than you think. But if you use the standard method, essentially you'd get back C hat equal 0.49, R hat equal about 1, and mu around 4.55 using this simulated data. Now, of course, you could then change R and C, and you'd always be able to recover what the truth is. A little aside here, and I say something that's a little bit weird, but this is a perspective that you have to accept if you're doing that type of modeling. So if you write a statistical model, that's true of regression, but also true of structural, you will always assume the statistical model is correct, that it is a true data generating process. And so while we're doing this, the only thing we're saying here is, suppose the world works as I stated it in the theory, then is it true that my estimator is doing what it's supposed to do, right? So that's what we're testing here. So a very simple approach in which we have used very little. The only thing we've used is a first order condition. Of course, we did solve the model, but only in order to simulate data, right? But for the estimation proper, it didn't solve for mu. Yeah.
So in writing and submitting structural papers, that's the usual criticism. The first criticism I get, you're assuming that your model is how the world works. So what is your response to?
Oh, but it's the same. The response for that is that's a statistical statement. So if you write a regression, and you write, these are the controls, this is one square term here, but not square root, or no square terms, then you will be assuming this is a correct model. So a specification is always descriptive of the world. Now the subset of that question is, it's a very important subset, because you're making a detailed set of very explicit assumptions under structural, it's certainly the case that assuming that this is close enough to how the world works might seem quite demanding. And close enough is very important. You never, even in regression, would never say this is exactly how the world works. Lots of things going on. But the close enough is important. I would tell you a perspective that many econometricians have, so I'm repeating it here. What we're trying to do here is to be able to be precise enough so that if it doesn't work like that, we know what we could be doing to make it work better. Example, suppose I apply that on the data and the numbers don't make sense. I get negative risk aversion. Maybe I should go back and say my exponential distribution is the wrong way. Maybe I shouldn't do exponential. Maybe I should say, oh, I only use earnings as performance measure. Maybe I should generalize it to earnings and price. And so when you're becoming explicit, it's giving you ideas about, what can I try and put in, and then what would be reasonable ways to make it fit the data. So there's always a dialogue between model and data. Now, to follow up one more way on this, because I had this conversation with other empirical colleagues, there is a risk of doing this. You think the model doesn't work? Well, you fix it. Of course, this is the dialogue that you're doing. So you fix it, and after a while, even the model is really not descriptive, it's going to work if you fix it too many times. And this is a place that's dangerous because at the end of the day, you'll have to explain the assumptions also makes sense from an intuitive conceptual perspective, because the fact that it fits is itself by design. It's going to fit at some point. And so I think most people who do that type of work, they don't overemphasize the fit. They emphasize a reasonable fit. It shouldn't be too crazy, but they also emphasize this is a parsimonious way that does a lot with little. This is very important as well, right? But again, I'm not, I know this is something to have a dialogue with others. Yep, Wenjie?
The purpose of estimating mu, because you know what mu is, if you know what C and R is.
Mm-hmm.
Right? So what's the purpose of
So very good question. So what you could do, which is better, more precise, is to say, I don't want to estimate mu. Instead, I'm going to embed in my fitting procedures the mu that should come out of the integral. So what I can do is always solve for mu, the same way as I solve for lambda, and I don't let the data tell me what mu is. I only estimate what I couldn't solve for. That's great. It's more time consuming. It's usually less robust numerically. This is how many authors do it as well. So you always have a trade-off. The more you use the information from the model, the more precise your estimation is, right?
My concern is about identification. You really have a unique solution to that problem. If you have too many variables to solve for.
Yep, so another question you might have, and this is going beyond what I was trying to do here. A very important characteristic of a structural model is your model identified. And by identified, we mean, is there going to be another set of CR and Mus that are going to give me the same fit, right?
You have two primitives, right? The mu is something artificial.
Yep. So what applied researchers do, let's see. So the economists, they usually try to get models in which you can prove identification. Of course, if you want to prove identification, you're going to use models that are simple enough that the nonlinearity in those equations allow you to crank out all the stuff. So it's not always feasible if, for example, you're doing dynamic modeling, you can't really prove that the solution is unique. What people do in applied work, I've done a little bit of both, but what many people would do is just plot that function. Just show me this mu tends to be unique. Of course, that's one parameter. What you can also do is vary around your mu and see if you have multiple solutions. You can always try to seek multiple solutions. That gives you a numerical proof. It's not a proof, it's a numerical argument. But certainly it's telling you something. If there's something really not identified, you would see it. So at least it identifies issues. Yep?
Back to forecasting.
Yep.
So
Yep, so I will show you, we'll do that in more details. It's not yet the full thing. My preference, because it's easiest, is to do bootstrap. Every time you want to do standard errors on parameters, bootstrapping it is the simplest way to proceed. So you simulate lots of samples, you estimate a lot of simulated samples, and then you plot the standard errors of those simulations. So it's called bootstrap, and the reason it's very lazy, I like it, it's lazy, is that you don't have to do the math of rederiving all the asymptotic standard errors. The only thing you have to know is subsampling, estimating. The downside is it's not going to work in complex models that take days to solve, because you're going to have to bootstrap 200, 500, 1,000 times, and so if your model takes a week, you're going to need 500 weeks. That's going to take some time, but who knows, maybe you buy 10 computers, and good to go.
Simulate the data, you cross the epsilon, right? So that is the arbitrary choice of like how the variance of that epsilon, does that matter?
Oh, well, here obviously it's good, right? No, we don't need to do standard errors here. It's obviously very close, but suppose what's further, would you know it's sampling error, right?
I guess my comment is not fully understanding. They also like big economic significance.
Yeah, so if you did it on data, which is our objective, of course, when you apply it on data, then what I suggest to do, first thing is to subsample the data and estimate on each subsample. And then you build your confidence intervals out of this. In regression, of course, you don't need to worry about this because we have really nice closed form expressions for all the standard errors. So why would you do bootstrap? But here, not closed form. It's complicated nonlinear equations. Sometimes you would need to do non-parametrics. So for example, you could fit f of x given 1/2, this CDF, PDF. You could fit it from the distribution of the performance measure. And so then you would be first pre-estimating the distribution of the performance measure, then plugging it in, two-step estimation. How do you do asymptotic standard errors for a two-step procedure? Well, it can be done, but it does require a lot more math. So bootstrapping solves the issue. All right, so second method, totally different approach. Let's still fit something about the model, but instead of fitting point-wise, and this is the worry, yeah, I can fit point-wise, but maybe some points are crazy. Maybe a point, you went out of control. I mean, a CEO, maybe there's Steve Jobs there, or maybe there's someone else, and I don't want to give too much weight to one point. Maybe it's an outlier. And when I'm doing this quadratic form, of course, if one point is completely wrong, then my model will go crazy. I don't want that. I want something robust. That's why many authors like method of moments. And what method of moments is doing is say, I'm not going to try to fit point-wise. Instead, what we'll try to fit is moments of the data. Moments of the data. All right, so how do we do this? Well, essentially, what I can do is to run moments of the data. How would I do this? I would calculate the value of the moment in the model versus the value in the data. And that's how I would try to fit these values. So I can use my simulated, yeah, so I would try to get the moments in the model and the moments in the data to converge. So I'll show you the code and what it does. But I want to first, lastly, show you the last method, maximum likelihood. And yet another way you can approach the problem is very similar to try to match the pointwise equation, but it's doing it in a way that's statistically more sophisticated. So what could we do? Well, we could assume that it's true that the model won't explain the data perfectly. Well, that's true, and why would it not? It's like a regression. There is an epsilon term, always a bit of disturbance that comes in every time you write your theoretical W. So on average, it's okay, but it's not okay for every point. So what would you do then? Well, we know that the likelihood of the model is going to be the difference of my data point, my simulated data point, minus the W of the model. And the likelihood, of course, is according to the distribution of the errors. So I plug this distance into my distribution of the errors. In that particular case, I say it's normal. And then instead of squaring the differences, I use a likelihood function by using the normal PDF as how I measure my distance. So in that case, I would have an extra parameter to estimate, which would be sigma. Sigma will be the noise, how big my errors are. This is what you do if you do time series. When you do time series, it's essentially most of the implementations in Stata and other software would use a likelihood-based model. So you would plug in the differences between the linear time series model and plugging these differences into normal errors. There is an advantage of that method and a disadvantage. The advantage is that MLE is the most efficient asymptotically way to do it. If you know the distribution, there's not going to be asymptotically another estimator being more efficient. The disadvantage is you got to know it's normal. And that's a pretty big assumption. You have to know the errors are normal. There's no reason for the errors to be normal. There could be something else, and if you estimate that normal model, you might get it wrong. So it might not be efficient. All right, so again, I'll post you some code. All the three pieces of code give you the same benchmark parameters. And essentially, little summary here before we break. I'm going to finish a little bit in advance. All right, full screen. So for estimation, you don't need to solve a model completely. It helps to solve a model. It makes you be more precise. And indeed, when you're solving a model completely, you're acting like a theorist. But it's more work. But in a way, the data will help you solve the model. And using the data will be a lot quicker and will require less transformation, less algebra to get to the results. In this example, we didn't solve the model in order to estimate it. We solved the model in order to simulate it. So that's one thing. The second is that what you're doing is writing a couple equations. So you're saying, hey, my theory said that equation should be true. And then you're putting in those equations the blocks that you see in the data. And you're trying to see, is that going to restrict the data? Is going to provide restrictions on what the data should or should not satisfy? Lastly, this is an advice when you start. And I think it's a very important piece because you never get to start if you don't do this. We always start with the simplest model. So the logic that we've applied in the 3 talks is the same here. You start from the simplest possible approach with a minimal set of ingredients, and then you let the data guide you. The data will tell you this model is sufficient, it's doing a good job, or this model doesn't do well. It's also going to tell you why the model failed. So if you look at my lambda, I very much doubt that my lambda hat would be equal to 1 over r hat in the data applications. And so then you might wonder what ingredients you didn't put in the model. In a way, the same discussions we have in theory hold on here. We're not trying to get a descriptive model. That's not the point here. We're trying to get a good approximation, a summary of what the data is. And so here we're only adding those extras, which could be, for example, having more general distributions or multiple signals, but being guided by what the data looks like, being driven by the anomalies. So I've worked on a couple of papers, and when you're going back to the act of sending out this type of paper, it's very important to be honest about what the model doesn't fit very well. It's good. It should fit certain things well. You can't just send out a paper that, oh, I didn't explain anything, but I'm feeling pretty good about it. No, really. I've worked so much, and no, it should fit certain things. You write a model, you want to say that it's not just something from your imagination. However, no one will believe that a simple model should fit everything. I mean, it would be great that you'd be like in physics, or you can narrow it down something. It's not the case. In fact, what people are expecting, it identifies places in which the model failed and why. And even that you might not do it in the same model because it becomes really bulky with lots of pieces, just understanding where we have to do the research and the theoretical research is one place that is a big benefit of doing structural. So in a way, you're telling a theorist, give us better model of this and that. This is what needs to be done. And so this is something that's, again, not fully appreciated if you don't do structural. Yeah, oh, sorry, yeah, I didn't see you.
So you have to be careful about, it sounds like you're letting the data tell you where to fill and how to fill with these additional features of the model. But, it sounds a little bit like changing your theory as you don't find the results that you like. Can you differentiate between the two? Tell me why it's okay here, whereas, if an empiricist doing a reused form paper said, I didn't find the predictions of my hypotheses to be correct, so I changed the model.
Mm-hmm.
That wouldn't be okay. But why is it okay here?
So I think the guidance, and because you're so much more restrictive and you're much more explicit on the assumptions you make, is that the discipline that you impose to yourself in terms of changing the model, like for example, you say multiple signals. So in my view, you rely on, oh, this disappeared. Anyways, you rely on theoretical guidance. So you try to anchor it to some extent into clear theoretical guidance that to you should make sense. For example, the ideal way would be to say, well, my model is from 79, but of course today no one uses from 79 as a baseline for what agency contracts should look like. So maybe I should look to the most popular theories, like a multi-agent theories, a dynamic theories, and this would be the first places where one would look. Price versus earnings is also a very accepted type of theory. You have choices, but these choices are not infinite, and they're not without cost. It takes a long time to rewrite the entire thing, and so the choices you make are not totally free.
So you don't have to have this all laid out in advance before you see the data. It's okay to let the data tell you sort of which direction to go.
I think ideally you would like to, there's no vehicle for that, but of course ideally you'd like to say these are the steps we take for sure. You know, if we had such a system, it would be such a more transparent system. Oh, well, this is gone. But so there's one place which I think we've lost a little bit of discipline, if I may. And the issue I'm seeing as a theorist is when we do these additions of assumptions, we always want to say, yes, I explained that because I was targeting that, but do I explain something more, right? You never say, that's it, I added one ingredient, and you see, this is going back to the parsimony that we were discussing at Stanford. If your model is really clunky with maybe 10 parameters, 15 parameters, and you explain 15 things, that on its own is not surprising, right? And you will see that in physics. So in physics, you got, I think, 25 parameters for the model. Maybe you know better than I do. But they explain hundreds and thousands of observations. And so the ratio of number of parameters to observation is enormous. And to me, we try to max out the ratio of the two, right? So with structural, because you can simulate your model, you could essentially investigate anything. You know, you want to know about this moment. Do we do a good job? Simulate it away. You know, you want to know about this variable. Well, let's see how it goes. And indeed, you know, that's what you want to do.
Jeremy, isn't that the approach you're going to have to do with ever-increasing amounts of data that are coming out now? Data that didn't exist even 5 years ago that's available today, and tomorrow it's going to be 10 times more than it is at this moment. And so I think you're right. If you go into it with the perception that this is all there is, and these are my choices, I'm going to test those out, you're really going to be missing a lot of forms of data that you would just simply have no idea exist, but for turning over those rocks.
Yep. Yeah. So there is plenty of places where you can check if your model is doing a good job. You know, it's not out there. You know, there are many. So if we can explain a great number of empirical facts with 20 parameters, I'd say this is amazing, right? It wouldn't be a clunky model. You know. Oh yes, Mario. Anyway.
Let's say, you know, I observe a phenomenon, and I think more hazard is writing the results. I write my model, I do my spatial estimation, and I can think pretty well what's happening. And then another person comes in, oh, I think this is an adverse selection problem, and it'll do exactly the same thing. And it'll probably also fix the data pretty well. How do you go out of these two things and say, well, I think, so like, wouldn't we have to create a model that embeds all of the things, or can we still survive with two different approaches?
No, man, that's what it's a very interesting thing that you can, if you're originating a new idea, you might say, let me estimate a model that has both pieces, and see quantitatively which one has to be stronger in order to explain the data. So that's one thing you could do.
Yeah.
Another, yeah?
By doing that, you lose the simplicity of each individual model, and you will end up having something very complicated that will face the problems that will.
And then you have to look for other things. You know, ideally, again, in an ideal world, the more complexity you put, the more things, the higher bar you put on your theory. Yeah? And then so another thing you can do if you have two models, so we talked about more hazard versus adverse selection, is to look at facts you didn't go after necessarily and see how each theory goes at each fact. And so many people in macro, for example, some work with search models, others work with mostly neoclassical, and they'd say, hey, what is the fact better explained for each? And of course, everyone has his own facts. Say, oh, my facts are better than your facts. But in a way, that at least encourages dialogue on what works.
In that example, you can estimate parameters in both models simultaneously, I think. So you don't have to come up with some meta model to capture both moral hazard and adverse selection, you keep two simple models and then say, okay, data, do you feel more strongly about the parameters in the moral hazard model, or do you feel more strongly about the parameters in the adverse selection model?
Yep, so that's the simplest way. So I can tell you I have a paper that estimates disclosure theory. And what we did is we have indeed a meta model that has both dye-like frictions and Vorecchia-like frictions. And so what you can ask yourself is, what if you neutralize the dye friction? What if you neutralize the cost? And how much explanatory power does each do? And so that at least measures relative to one another. We're not testing here. We're just saying what theory seems to be the most important here. Well, they're both important. That's what you get at the end. Now going back to this, I want to conclude on that. There is another place where I really think that structural has a good way to approach it. Sometimes you have tests that you do in reduced form that has, is it theory A and theory B? But often you know that the data is certainly A plus B. And they're not opposed. They could both be going on at the same time. And so how do you test for the A plus B? And I have to say something about the degree of A versus the degree of B. It's not a yes or no question. And so here again, you need to assume a lot more to kind of get some insights. Last point, and I'll finish here for today, because just an introduction. Always be aware that assumptions have cost. You know, it's trivial to say, but assumptions have cost. And so when you're making those assumptions, you're reducing your confidence. And so you have to be aware that how do variation in assumptions change the results. And this certainly is going to be true. And what you learn by doing this is having a sense of what assumptions lead to where. And certainly people have preferences about what they think is more important than another. So sensitivity tests, even if it's not a fully robust result, are themselves teaching you something. You know, if you believe this is the right way of thinking about the problem, this is where it should land. So that's something that's always forgot. When people read structural, they say, well, that parameter is 10% or 20% or 30%. Plus all the standard error, of course, but also the model noise, the uncertainty about the right model. And so you might write different model in order to see where things lie out. So, you know, don't misunderstand when you see someone giving you an answer to a fundamental question like it's 12.2 or 14. What they mean is within the narrow scope of one model, we know that this would be the number, but of course we hope to conclude this by looking at different models. All right, so I don't want to be too philosophical. You know, we're going to stay technical from now on, but we'll revisit that on Wednesday. So Wednesday, we'll spend all our time on doing more structural. Thanks.